Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and going to be talking about different types of stability or different types of instability. I guess you can describe it either way. But basically the concept of stability, and for me, the best analogy has always been a ball at the top of a hill, okay? The ball is stationary, it's sitting there, and if you give it a little nudge, then it's going to roll faster and faster down the hill, never to return to its initial location, okay? So we call that instability in the sense that if you displace something and it just rockets off, never to be seen again, then that's instability. Now, stability would be analogous to a ball at the bottom of like a valley, okay? And so you push that ball up the hill a little bit, and then once you get done pushing it, the ball says, I don't really like this that much, I'm just gonna go right back to where I started. And so stability means you displace something and then it comes right back to where it started, and the net result is no movement. So think of it that way, that with a thunderstorm, you give an air parcel a little nudge and it just goes boom, like that way up. And if it's stable, you give it a little nudge and it says, nah, I'm not going there. It comes right back down to the surface. Okay, so let us move on here and talk about this. And every time I show this diagram, I get scared that I'm going to scare you. But this is what we call a skew-T log P chart. That stands for the fact that the lines of constant temperature are skewed. They're not horizontal or vertical, but they're skewed. And I'll show that to you in just a second. And then the log P means that the mass of the atmosphere is actually distributed in a logarithmic sense, that most of the mass is pulled toward the lower levels because of gravity. So the most dense air is near the ground, and then it gets progressively less dense as you go up. And you can sort of see that when you take a look at the lines of constant pressure here. Okay, and I'll take myself out here just briefly so you can see all of this. You notice how I've labeled this in intervals of 100 millibars, but you notice how those labels get farther and farther apart as you go up, which means the same amount of mass is occupying a greater volume, so the density is going down as you go up. Okay, so now that we have this chart in front of us, these dotted red lines are lines of equal temperature, okay? And they're labeled in Celsius, so you've got like minus 10, 0, 10, 20, 30, and so forth, okay? But just remember the lines of constant temperature are angled like that. Then we have lines that are called dry adiabats, and what that means is that if an air parcel begins to rise, or sink for that matter, it's going to change its temperature by moving along those lines. And roughly it's about 5.5 degrees per 1,000 feet, okay? So if the air parcel begins to rise and it's dry, in other words, not saturated, then it is going to cool at a pretty good rate. And you'll notice that these lines are almost perpendicular to the lines of equal temperature. So it's a pretty decent lapse rate. Things get cooler in a hurry. And then we have these lines, these green lines, which are called moist adiabats, okay? Now, if an air parcel is saturated or becomes saturated, then the process of condensation actually releases heat. And so now it's not going to cool at as rapid a rate as it would if it was unsaturated, okay? And so you can see like down in here where the temperatures are fairly warm, here's the dry adiabatic lapse rate, and the moist adiabatic lapse rate is quite a bit different, okay? Now, another interesting thing before we move on here, do you notice how as we get to the colder temperatures, the moist adiabatic lapse rates and the dry adiabatic lapse rates become almost parallel? Why is that? Well, there's so little moisture in the air when it gets to be very, very cold that there isn't enough mass of water vapor to release all that much heat due to the process of condensation. So once you get into those really, really cold areas, then it's basically a wash. The dry adiabatic and the moist adiabatic lapse rate are virtually the same. Okay, so now let's move on and talk about these 3 different types of instability. So let's say that we have the dry adiabatic lapse rate, so that's the rate at which an air parcel would cool as it goes up or down. And then the actual lapse rate looks like this. Now, we call that a super adiabatic lapse rate because the lapse rate of temperature is even steeper than the dry adiabatic lapse rate. Now, you're unlikely to ever see it extend over this much of a depth of the atmosphere. This is most likely going to occur right near the ground, like if you have an airport runway, for instance, that absorbs solar radiation very, very effectively, then you might have a super adiabatic lapse rate in the very lowest few feet or tens of feet in the atmosphere, okay? But you're not going to see it much above that. I'm just using it here for illustrative purposes. So let's suppose we have a little air parcel, which I'm going to denote by this circle here, and it's going to move along the dry adiabatic lapse rate, okay? So it's going to go up like this, and you'll notice that because of the lines of equal temperature being skewed, it is going to be warmer than the environment that it's in. Okay, the air parcel is moving along the blue line, the red line is the environment, and so it is warmer than its environment, it is buoyant, and therefore it is going to accelerate upward because buoyancy is a force, okay? And really, if you think about it, this is the way that a lot of thunderstorms can get started, where if you have that super adiabatic lapse rate in the very lowest part of the atmosphere, that's all it takes to get that air parcel to become buoyant, and then if it keeps rising in the environment, in other words, if it stays warmer than its environment, it's going to continue to accelerate upwards. So this is what we call an absolutely unstable atmosphere. Then there's one called conditionally unstable. So here's our dry adiabatic lapse rate, just like in the previous case. Then we have the moist adiabatic lapse rate, okay, denoted by the green line there. And let's say the actual lapse rate is the one that is in red there, right in between the two, okay? So if an air parcel is unsaturated, it is going to move along the dry adiabatic lapse rate, and it is going to be cooler than its environment, and so therefore it is not going to rise. In fact, if it even starts to rise, it'll sink right back to its original location. However, if the air parcel is saturated, it's going to move along the moist adiabatic lapse rate, and it is going to be warmer than the environment, the actual lapse rate. And so therefore the force of buoyancy would drive that air parcel at a quicker and quicker rate. In other words, it would be accelerating upwards. So in a conditionally unstable environment, the actual lapse rate is between the dry adiabatic lapse rate and the moist adiabatic lapse rate. And then we have what's called an absolutely stable environment. So here is our dry adiabatic lapse rate, here's our moist adiabatic lapse rate, and the actual lapse rate is like this. Great example of this would be an inversion, where the temperature actually increases with height. You'll get a lot of this on a clear, calm night, especially in the wintertime, where the temperature will cool down right near the ground, but just above the ground, it's actually fairly warm, okay? And so as soon as the sun comes up, it rapidly wipes out that inversion. The temperatures jump very, very quickly, and then the rate of temperature increase the rest of the day is much slower. But the bottom line is, if you have an air parcel in this kind of a situation, and it moves along the dry adiabatic lapse rate, clearly it's going to be colder than its environment, so it's not going to continue to rise. And even if it goes along the moist adiabatic lapse rate, it's still going to be colder than its environment, and so it will not be able to continue to rise either. So if the temperature is either constant with height, or only decreasing slightly with height, or increasing with height, that would be a situation where it would be tough for an air parcel to continue to go up, because more than likely, as soon as it started that process, it would end up being colder than the environment that it's in. All right, I hope that made a little bit of sense. That is bonus weather video number 2 for this week. The third one will be coming up on Friday, and the next daily update, the short version is already out. The longer version will be out before too long. And when you get done watching all of that, then I will have a date with you tomorrow. So you all take care, folks, and we'll talk to you soon. See you later.